Okay, so the initial value problems. These are the ones, if I have an initial value, an initial condition that I know that my function that I'm trying to find, I have a derivative, I'm trying to find my original function, I know that it goes through this ordered pair. These are the ones that are going to allow me to actually solve for the numeric value of c. So instead of having the general antiderivative, if I have an initial value, I can find the actual c value. I can find which specific function I was looking for, okay? There are some relations where this might come into play. So let's see. Blank is rate of change of position, okay? Velocity. Okay, so we know that velocity and position are related, right? Velocity is rate of change. Rate of change means derivative. Let's not beat around the bush here. Derivative. Velocity is the derivative of position. So if we go vice versa, that means that position is the antiderivative of velocity. Right? Blank is the rate of change of velocity. Acceleration. Acceleration is the rate of change, which is slope, which is derivative, of velocity. So that means that velocity is the antiderivative of acceleration. We spent the most time in derivatives talking about those two, but we also talked about the rate of change of cost, which was the marginal cost. Marginal cost is the rate of change of cost, so that means that cost is the antiderivative of marginal cost. Oh, what's the rate of change of force? Actually, I just drew a blank. Hold on. Rate of change of force. The derivative of force is... I lost it. I don't even remember right now. Does anyone know what the rate of change of force is? I'm going to Google it. What's the derivative of force? I forgot. What's the derivative of force? Google did not understand me. No, Google. That was not useful. Oh, it's work. Or, no. Okay, this one is, okay, force is the derivative of work. That one I know. So the derivative of force is potential energy? Energy? Energy. I'll go with that. Yeah, I'll go with that. Okay. Energy is the rate of change of force, so that means that force is the antiderivative of energy. Force is the rate of change of work, so work is the antiderivative of force. And what's the rate of change of volume? Area, or surface area, but it's area. So volume is the antiderivative of area. Okay. So we did spend time previously mentioning those three at least, right? We also mentioned this one a little bit, right? Okay, in some of our story problems. I forgot about these two. We didn't spend a whole lot of time with these two, but you can definitely see how they tie in with physics, right? And so that's why there's all the physics classes that maybe you haven't taken yet, or calculus-based physics, because we got to have the relationships. If we're going to be dealing with force and work and energy, we need to have our calculus to be able to relate the three things, just like we do for velocity and acceleration and position.
We could do it without calculus. It would just be a lot more work, wouldn't it?
Well, it would be a lot less accurate, really. You can do it in special cases, right? So you can do it in special cases if you restrict certain variables, or like you say, you're working with a two-dimensional distance or a three-dimensional distance. But as long as, when you start changing how many parameters you have, then you're going to really start needing to differentiate to be able to find the derivative or the way the particle behaves in that specific case, right? We generalize things, like we generalize projectiles, right? Like, because we can say how a projectile always behaves because it only has one force affecting it, gravity. But once you start throwing other factors like a variable wind speed or things like that, there are too many factors to generalize it, and so you have to use your calculus right in a certain problem. So if you can generalize it, we can get away from using the calculus on it. So you do that. There is some physics that it's algebra-based because we can give you a generalized formula for certain cases. But if you start having more variables involved, then you're not able to generalize as often. Anyway. The three that we use most commonly are the acceleration, velocity, and position. So just a diagram again of the relationship. If we have our position function, if we take the derivative, then we go down, right? The derivative of position is velocity, the derivative of velocity is acceleration. And if we take the antiderivative, we go up. The derivative of acceleration is velocity, or the integral of acceleration is velocity, and the integral of velocity is position. So we can start and differentiate down and start and integrate back up. Okay, so they are just interrelated, the three of those. Okay, so we talked about what we're going to do with our initial value problems, and we're actually going to see an initial value problem on the next page. This is one where we're talking about projectiles. And in this case, okay, so we throw a ball from an initial height upward with some initial velocity. And we've already mentioned the general formula, I think, when we were in some section in Unit 2 or 3, right? We had a general formula for that. But we're going to get to that formula just from the fact that if you have a projectile, the only acceleration that affects it is gravity. Okay, after it's left its launching point, it's not accelerating on its own anymore. It's not propulsed. It's just being affected by gravity. So if I start with this gravitational constant, negative 32 feet per second is gravity in feet, then I can find the velocity and the position function by integrating it. So the velocity function is the antiderivative of the acceleration function. And so I have to do the antiderivative of negative 32 dt. Okay, and that's going to be negative 32t plus c, because 32 is a constant, right? So if I take the antiderivative at one time, negative 32 times t, if I do the derivative of negative 32 times t, I'm back to negative 32 plus c, right? Then it's a matter of what that c means, right? So if I note that v of 0 is 0 plus c, that means that c is, you get c when you plug in 0, right? So that means that this is the initial velocity. So we're going to call c v naught just to stand for initial velocity. Okay? So that changes our v of t equation to negative 32t plus v naught. Does that make sense? Okay, what we're looking for is a position function. So I know that position is the antiderivative of velocity. So if I take negative 32t plus v naught and I integrate it with respect to t, that's where we get the derivative of negative 32t is negative 32, okay, t, add 1 to the power, t to the 2, divided by 2, negative 16t squared, yep. Then plus what? The antiderivative, or the integral of v naught is v naught t plus a new c, right? Okay? So if you plug in 0 again, s of 0 is 0 plus 0 plus c. It's c, right? That means that that c is the initial, because you plugged in 0 for s, it's the initial position. So we can call that second c s sub 0 for initial position. That means that s of t is negative, we'll just write 16, because we got 32 divided by 2, t squared plus v naught t plus S naught. And that's the same equation that was up there. That's the same equation that you were given in the projectile section of when we started doing our derivatives, right? Where we were saying if you had a projectile, you're able to write the initial position function. And that's kind of what we mentioned before. You were asking, like, there's some things you can do without calculus, right? Because if it's a projectile and there's no acceleration happening on it, then you can get, in general, what the function is just because someone else did the calculus for you and it always works this way, right? It's not that it's not using calculus. It is using calculus. It's just someone else already did the calculus for you. We can say this is the formula, right? But if you don't have a rock as your projectile, if you actually have a rocket as your projectile where it does accelerate, then this changes and you can't use this anymore. So then you're going to need to do some more calculus work with that based on an acceleration function, not just a constant for the acceleration. Okay. All right, so we can just generalize here again. The acceleration function for a falling body is a of t equals g, being gravity, right? It's just gravity here happened to be negative 32 feet per second. That's the gravitational constant we use here on Earth, okay? But it's just in general, it's g, whatever gravity is. So if instead of the 32, you had g everywhere, so this would be now gt plus v naught. This would be g over 2t squared plus v naught t plus s naught, right? Okay. Knowing that g is always negative, right? Because I didn't write my negatives because I assume that g is always negative because it's a downward force. All right. Now we actually get to use this on the next page, I think.